Hi, in this video, I will be showing you problem number 3 of chapter 16, section 4. Evaluate the line integral by two methods, A, directly, and B, using Green's theorem. Integral over C, x, y dx plus x squared y cube dy. C is a triangle with vertices 0, 0, 1, 0, and 1, 2. So we are asked to evaluate line integral in two methods. One directly, the other one is by Green's theorem. So we have to know what Green's theorem is. Let C be a positively oriented, piecewise smooth, simple closed curve in the plane and D be the region bounded by C. If P and Q have continuous partial derivatives on an open region that contains D, then integral over C P dx plus Q dy equal to double integral over D dou Q by dou x minus dou P by dou y dA. Dou Q by dou x is partial derivative of Q with respect to x. Dou P by dou y is partial derivative of P with respect to y. Here F is Pi plus Qj. The line integral over Cf dot dr is integral over C P dx plus Q dy. Now, let's graph this triangle C, enclosed by the boundary C, the triangle, with the vertices given in the problem. So one vertex is 0, 0, the other one is 1, 0, the third one is 1, 2. So let's plot these points and graph this boundary C of the triangle. And we'll, because in Green's theorem, when we apply, we have to have it counterclockwise direction. We also know that it's 0, 0 to 1, 0, the first line segment. We will call it C1. And the line segment, directed line segment joining 1, 0 to 1, 2 as C2. Then line segment, directed line segment joining 1, 2 to 0, 0 as C3. So C is made up of C1 plus C2 plus C3. So now we are going to evaluate this line integral directly. So using the C1, C2 and C3. So integral over Cxy dx plus x squared y cube dy equal to integral over C1 plus integral over C2 plus integral over C3. So where C1, C2, C3 are as shown in the picture. Now, we will find out the vector equation of each of these line segments. Vector equation of C1 is R, vector R equal to vector R0 plus T times vector R1 minus vector R0, where T lies between 0 and 1. So if we use that, because the first point is 0, 0, the second point is 1, 0, using their position vectors, we get the equation in this form, which is T times vector component 1, 0. So using the parametric representation of this vector equation, we get x equal to t and y equal to 0. Now the parametric equation of C1 is x equal to t and y equal to 0, which will give us dx equal to dt and dy equal to 0 dt or just 0. And t lies between 0 and 1. Now, similarly, we have to find out the vector equation of C2 from their parametric equation and vector equation of C3 and its parametric equation. So it's a directed line segment. C2 is the directed line segment from 1, 0 to 1, 2 in that direction. So R equal to R0 plus T times R1 minus R0 in vector form for C2 will give us, here R0 position vector is vector 1, 0 plus T times, if you subtract R1 minus R0, it's vector 1, 2 minus vector 1, 0, which will be 1, 0 plus T times 0, 2. So R equal to, now if you write this vector equation, it's going to be 1 plus T times 0 plus 0 plus 2T. In parametric equation of C2 would be x equal to 1 and y equal to 2t. So dx equal to 0 dt, dy equal to 2 dt, and t lies between 0 and 1. Similarly, we have to get the parametric equation of C3. So first we'll start off with the vector equation of C3. So the directed line segment joining 1, 2 and 0, 0. So vector R equal to R0 plus T times vector R1 minus vector R0. Using that, we will get initial point here is 1, 2. So vector 1, 2, position vector. Then T times R1 minus R0, that is 0, 0 vector minus vector 1, 2. So R equal to 1, 2 plus T times -1, -2 in component form. So the parametric equation of C3 would be x equal to 1 minus t and y equal to 2 minus 2t. Now dx equal to negative dt and dy equal to negative 2 dt. Now part A is integral over c xy dx plus x square y cube dy, which is converting everything to parameter t, integral 0 to 1, then by substituting for x, y, and x square, y cube, and all that for along every path, on C1, C2, C3 respectively, we get on C1, we get the first integral. For C2, we get the second integral. So when you do C2, keep in mind, we have to write x equal to 1 and y equal to 2t. X equal to 1 and y equal to 2t. Same way when you write C3, we have to remember x equal to 1 minus t and y equal to 2 minus 2t. So integral 0 to 1, 1 minus t times 2 minus 2t times negative dt plus 1 minus t the whole square times 2 minus 2t the whole cube minus 2 dt. So we'll call it I1, I2, I3, I1 plus I2 plus I3. I1 corresponds to integral over C1, I2 corresponds to integral over C2, I3 corresponds to integral over C3. So we have to evaluate these three integrals. So integral over c xy dx plus x square y cube dy. The first integral is going to be 0. That is integral over I1 is going to be 0. I1 plus I2 plus I3, we are going to be evaluating each and every one of them. I1 is 0, I2 can be evaluated, which is integral 8 times t cube times 2 dt, which is 16 t to the power 4 over 4 between the limit 0 and 1. Which is equal to 4. So I2 equal to 4. Next, we have to evaluate I3, which is integral 0 to 1, negative 2 times 1 minus t the whole square, minus 16 times 1 minus t to the power 5 dt. We can easily differentiate this, integrate this by making a substitution, 1 minus t equal to u. So at use u sub 1 minus t equal to u or negative dt equal to du. So using that you will get 1 minus t the whole cube over 3 with the negative 2 in front, and also the integral will throw a negative 1. So we are going to do that as negative 2 over 3, 1 minus t the whole cube between 0 and 1. Then the second part of the integral is 1 minus t the whole power 6 over 6 times 16. All this between 0 and 1. If you compute this value, you will see that to be negative 2 by 3 minus 16 over 6, which is negative 2 over 3 minus 8 over 3, which is equal to negative 10 over 3. This is what we got by direct method, which is much longer. Now we are going to do the same thing with by using Green's theorem. You will see how the problem becomes so simplified if you use Green's theorem. So for the first part, I1 is 0, second part is 4, I3 is negative 10 over 3. So if you simplify, it's going to be 2 over 3. So this is the answer for the first part of the problem. Now we will do by Green's theorem, the same problem with Green's theorem. So the method of Green's theorem in this case, so integral over c xy dx plus x square y cube dy equal to double integral over d, partial derivative of q with respect to x minus partial derivative of p with respect to y dA, where d is bounded by the curve c and the c is traversed counterclockwise. Dou p by dou y equal to x and dou q by dou x equal to 2xy cube. As we need the domain D now, we will recreate the same graph here and look at the domain. So domain is the inside of the triangle here. That is what the domain is. So Cartesian equation of the line join of OB would be y minus 2, then slope multiplied by x minus 1, y minus y1 equal to m times x minus x1. That will give us y equal to 2x as the equation of the side OB in this triangle. So y here runs from 0 through 2x. So integral over c xy dx plus x square y cube dy is double integral over d over the domain. And we are going to use the derivative dou q by dou x minus dou p by dou y. So if you substitute those values that we got in the earlier slide, dou q by dou x minus dou p by dou y, dou q by dou x is 2xy cube, dou p by dou y is the x. Substituting that, we get double integral over d 2xy cube minus x dA. Then it is integral 0 to 1 integral 0 through 2xy cube minus x dy dx. So if you first integrate, notice here y is ranging from 0 through 2x. This you can see from the triangle that we drew. Then it's integral 0 to 1. You first integrate with respect to y. That would be 2xy to the power 4 over 4 minus xy between the limit 0 and 2x dx. Then it is integral 0 to 1 xy to the power 4 over 2 minus xy between 0 and 2x. If you integrate now with respect to, substitute for y now, the upper limit and the lower limit, and we get purely an integral purely in terms of x. Then integrate with respect to x and plug in the limits 0 and 1. You get 4 over 3 minus 2 over 3, which is equal to 2 over 3. Thus we get the same answer, but with the Green's theorem method, the problem looks much shorter than the previous method by evaluating the integral by direct method. In my next video, we will be discussing one more problem based on Green's theorem to evaluate the line integral, where the curve given would be a positively oriented curve. Hope this video helps.